Good morning, and well, thank you very much for this nice introduction. I appreciate that. It's a really great pleasure to be here. It's my first time, and although I have a kind of substantial, long history connection with Turkish researchers, I don't know how many of you know Mete Atatürk, who is the professor in Cambridge. He was my first PhD student in Boston when I came there in '96. So we had 6 years of nice research, after which he went to Europe and was successful. And he demonstrated the level, the background and level of traditional education in Turkey that I really appreciate very much. Especially these days when the overall around the world in many countries the basic education is getting kind of watered down, you start to appreciate the good quality background education. And that's in particular one of the reasons I'm happy to be here and to talk about some maybe slightly more advanced issues associated with quantum optics, but I try to put it in the way that hopefully a majority of you will understand, and to show you the logical progression, how we can go from some basic things to a little bit more advanced, and to show how the research leads to new ideas, and the ideas lead to new technologies, and hopefully some of these technologies will see practical applications. All right, so today we'll start with the more like basics first, but we have to do that because you cannot do anything without basics. So actually, can I ask you if it's possible to turn off these lights to increase the contrast just a little bit on the screen? So today we'll start with what is the entanglement and why this is the central element of quantum physics. You may have heard, all of you probably have heard about entanglement. Entanglement, that's a kind of very mysterious item, very mysterious subject of quantum mechanics. Lots of discussion going around this since 30s in the last century when it was introduced, and there are lots of mysteries. I'll try to show you that there is no mysteries around there. If you study it long enough, you start to realize the concept is pretty straightforward if you understand it, but as usually after you understand something in physics, this something becomes your tool, and you can start doing engineering. In this case, it will be quantum engineering or quantum entanglement engineering. That will be the subject of the second lecture. All right. So I'll briefly talk about the what the even before the entanglement. Some few items that are important to remember, and which usually people brush aside. Many of you have heard about them when you study courses in quantum mechanics, but later on it's kind of washing away. But I want to remind them because this is important for understanding of basics of entanglement. Then what it is, what the entanglement, and what is quantum entanglement? Well, there is entanglement in general, and there is quantum entanglement. Then I'll talk about the qubit as a major element of quantum information processing and its relationship with entanglement. Then we'll talk about the physical foundations of quantum entanglement, like relation and experiments to verify it. And I'll show you that there is no any paradoxes in quantum mechanics. You may have heard about paradoxes in quantum mechanics. They're all artificial and made. There is no paradox. And specific requirements for quantum entanglement engineering. That would be a kind of introduction to the next lecture, how to implement those requirements in practice. Well, the good point to start would be the postulates of quantum mechanics. Why I'm starting with this? Because if you remember, well, the different textbooks are put them in a different order, but all of them are present there, either this way or around, it doesn't matter really. Basically, an isolated physical system is represented by the Hilbert space known as the state space of the system. The system is completely described by a unit vector in this space called the state vector. What's important here is state vector and isolated physical system. Remember that. I will talk about this several times today. And it's one of the very important properties of quantum mechanics. A system must be isolated. No energy in, no energy out. Isolated quantum system. That's where all the internal operation of that system fully described by quantum mechanics, and all the apparatus of quantum mechanics is fully applicable to that system. Evolution of the quantum state. The evolution of a closed quantum system is described by unitary transformation. Transformation is unitary, which also means it's reversible. But again, you need a condition. The system has to be isolated. And basically, this is the vector, state vector psi, wave function, as you know, that's a state. And if you have original state, you act on this state with the evolution operator, you will get the final state out of that. Then measurement of the quantum state. That's important too. Basically, it's a measurement operator. It projects the state of the system. Well, on what? It projects it on the classical measurement device. You basically, by any measurement, you're going out of the quantum domain. You're not there anymore. So that's where the boundary is. The minute you do the measurement, you're out of the quantum domain. All right? And the composite systems, well, basically, if you have several systems, you try to consider several of them. You just have to add them together as the tensor product of the vectors. So that's the basic postulate. I hope I made enough emphasis on the isolated system. That isolated system is defined by these parameters. Now, one of the most important kind of notions in quantum mechanics is Hamiltonian. What is the Hamiltonian? Well, the quantum mechanics is still mechanics. Those of you who studied originally theoretical mechanics, real mechanics, theoretical mechanics, you know, so you got the Lagrangian first, and then you get Hamiltonian, right? Lagrangian is the difference of kinetic and potential energy, but Hamiltonian is the sum of them. So it's a total energy of the system from the physical standpoint. Okay, and because it's a total energy system, so the system of quantum, the energy of quantum mechanics system is described by that. And evolution of quantum mechanics system also described by the Hamiltonian. We'll see this in a minute. The question is how we perform experiments on closed systems. The system is closed, as we said, but then you want to act on it and do something with that. How you do it? And the answer is very simple. In order to preserve the closedness, but you still want to interact, you have to do this, first of all, in a very small steps, and also not continuous, but in piecewise, in a piecewise constant manner. So basically, you change the Hamiltonian of the system, it's fixed, it's now closed, you do this calculation, you have all the parameters. Then you can change it a little bit more and close it and do the calculation. So that's how you do that. There is a limitation on the amount of how much you can change the system. Well, one of the consequences of this, actually, let me see. Yeah, of the quantum system evolution and behavior and unitarity of operations is that quantum mechanics is the linear theory. Well, no surprise, it's governed by the linear algebra. Linear. Remember every time, linear. If someone tells you, oh, we have non-linear effects, immediately it's not quantum. You can consider non-linear effects to be somehow quantum if you cut it in pieces, in small pieces. And within each interval, the disturbance is small enough, you can approximate it by the linear function. It's a well-known concept in physics, piecewise linear modeling of something. You have exponential curve, you can cut it in pieces, and within each of the pieces it will be linear. So it's very famous WKB approximation. That's what it is. You can have disturbance for the system, but it should be small enough to be still considered linear. And evolution of the system is defined by the Schrödinger equation, basically where a Hamiltonian defines the evolution of the wave function. And how it defines, well, we all know that this type of equation has this type of solution. It's a conclusion from every course in differential equations. It was very interesting. When I studied differential equations, I was very surprised. They give you differential equation and say, okay, here's the solution, it has to be searched in this shape, in this form. And my question always was, how did they know what form to find it? Well, then later on I realized that there were generations of mathematicians in the past who were applying this to many different problems, searching it, and then they found it. Now, as majority of you have taken differential equation courses, you know if you have this type of differential equation, that will be the type of solution. This type will be this one. So if you see equation like this, you know the solution will be exponential with these parameters, and that would be unitary if this is the really closed Hamiltonian, Hamiltonian of the closed quantum system. Well, dynamics of the system, of the quantum system, is defined by the dynamics, again, by the Hamiltonian, by the Schrödinger equation. So our wave function would be, final wave function is initial wave function, and this unitary transformation applied to that, where this unitary transformation has this shape. Well, the interesting question usually is, okay, I just told you it's a linear theory. How would you apply the operator that has exponential right here? So how we can resolve that? Basically, you have to take this and apply to this, and it has to be a linear function to find whether it's exponential. What should we do? Who knows?
We have to linearize by identity plus the first.
Yeah, you take a Taylor series of the exponential, right? Exactly this. So then when you take it, and you will have the first term will be linear, and that's exactly what you will take. Basically, that's how it works. And then operator defined as unitary. Unitary means the inverse equals the complex conjugate, so that's time evolution of the system. We all know that in addition to the Schrödinger picture of evolution of quantum mechanics, there is the Heisenberg picture. So the Heisenberg picture tells you, okay, if something is evolved, it's not the a function evolved with time, it's an operator that evolved with time. Basically, these two pictures are absolutely equivalent, and they go back and forth, whatever, like it all depends on what type of problems you try to solve, and what's your preferences in basically educational preferences, which you like more. So that's basics of quantum mechanics that we need to know. And now let's start talking about the entanglement. So first, let's do a little bit of history. So the Schrödinger introduced this, oops, sorry. Yeah, Schrödinger introduced this term in 1935. And it's really the definition of entanglement. It was the German, I'm not good in German, but my German colleagues, they told me that it's the same word that is used to describe this position, basically. Like, you don't see where is the one first, where is the second one. They are kind of mixed together in the way that it's hard to understand which part is which. You can see the general things, but you cannot separate them. So basically, the quantum system of two or more objects, could be particles, could be basic quantum objects, possibly spatially separated, not necessary absolutely, have to be described with a reference to each other. What does it mean? What does it mean? Reference to each other. So it means there is some relationship between them. And the formal mathematical definition is if your function of two particles, of two independent particles, then it will be just a product of two, right? And we all know from many courses in physics, whenever you have something interacting, but then you put this so far apart that this interaction is not valid anymore, then you can describe it as the product of two independent events, right? It's kind of a description of independence, simple product. Also in probability theory, that's what it is. It works, it comes from there, basically, because again, linear algebra and probability are two pieces of language that quantum mechanics is built upon. That's what you use all the time. Well, and then if you cannot separate them, if you cannot present it as a product, then they are entangled. It's just when you cannot do that. So basically it's non-separable is entanglement. That's it. Well, here I don't want to use this portion. It's for the mixed, this is for pure quantum state. For mixed states, it's all the same except that instead of wave function, you use the density operators. And the difference is very simple. So the kind of pure state is a well-defined parameters, and when you have a density operator, kind of spread. It's some distribution. But it's not important. Now, all right. So what do we have? We have a non-separability. So consider C is a system of two parts, A and B. Well, non-separability. But non-separability, it's a general mathematical term. It has nothing to do with quantum mechanics originally, right? We all know functions can be separable and non-separable, mathematical. Well, the classical physics has multiple examples of separability and non-separability. Basically, if you have a system combined of two systems, and it's a classical system, if joint probability is not equal to the product, what it means? It's correlated. That's what it is. If these two particles are so far apart, there's no any physical reason to be correlated, it's a product. If by any chance, even like mechanical system, you bring them close to each other, or electrical charges, you bring them close to each other, they start to interact, right? There's some interaction between them, and then relationship between them, right? So that's called correlation. So, it's absolutely classical parameter, but if you use the term non-separability as entanglement, then it is. But it's related to probabilities, real values, probabilities, right? Okay, what really quantum mechanics was about, what Schrödinger was about, is about the non-factorizability of wave functions. That's the difference. What's the difference between probability and a wave function? The main difference is? Exactly. You have amplitude and phase. And this is really the bottom line, what quantum mechanics gives you in addition to classical physics. That's it. The space of capabilities of different vectors you can generate is dramatically greater than combination of real numbers here. Why I'm talking about this, because this very popular, some people trying to make a kind of, they say, oh, we have classical entanglement. Okay, I know, like 20 years ago I had a graduate student, he came to me one day and he said, I brought you a gift of entanglement. What it was the kid's toy from the toy store. It was the, you know, like piece of rubber with the aluminum wire inside, and you can make all kind of knots around with this, and it was in a plastic bag. On the back it was called entanglement. Yes, it is, it exists, but it's not quantum entanglement what we're talking about, so don't make a research topic out of that. This is the real thing, and that's where the foundation of many, many, many things we're talking today about, quantum things, it's due to the fact that each element of this function has the magnitude and phase. And there are lots of options, and of course, each one of them at the end ends up with the probability. But then there are many more options than you can design from here. All right, qubit. Another big element of the modern quantum information and everything. So, what is a regular bit? Well, bit is 0 or 1. Mathematical bit, logical operation. 0, 1. It could be low voltage, high voltage, whatever you want. You can identify it and it will be like 0 and 1. All the mathematical, all the computational gates, they operate with it. They switch it from 0 to 1 under different conditions. You have AND gate, OR gate, NOR gate, all the gates you have, and all computers based on that. Well, every time you hear about the quantum information, they say, oh, that's because we have this qubit. All right, what it is, what this qubit is. Qubit, oh, of course, because it's bit, it has to have 2 states. The big difference, you don't know which one is definitely, which state this system is in definitely right now. It could be spin up, spin down, but you don't know. It's equally probable it could be this or that. Photon polarization is another equivalent of that. In fact, polarization of photons is a kind of expansion of spins into electromagnetics. Well, the only difference is there are 3 spins, X, Y, and Z, 3 orientations of the spin, but only X and Y polarization. Do you know why there is no third one? Where did the third one go?
Actually, there is a third one, but we don't. Propagation.
Yeah, propagation, and how fast it goes. Okay, what happens when something goes with the speed of light? It shrinks. So basically we have to know that. All right, so that's our tool. What it could be good for? Well, it's all started with originally when quantum computing idea was introduced, and then Peter Shor introduced his factoring, prime number factoring algorithms in '94. Well, it's too bad it's the only quantum algorithm we have right now. Still, only. Fully quantum algorithm. Love Grover introduced his search algorithm, which I call like half a quantum algorithm. So we have 1.5. Because this one does speed up, but it's not as kind of powerful and does not take so much power of quantum mechanics to do that as the Shor's algorithm, because this is really, in fact, for the last 30 years, that's what was funding all the quantum computing research. And we'll come back to that again later on when we talk about the quantum computing, so how much of this is left really today. But that's where the idea came about quantum computer. And quantum computer is something that will replace classical computers in factoring numbers. You need to have quantum gates, control node gates, similar to classical gates, but they will do something different because they are quantum control node gates and they're operating based on qubits. And we'll talk more about this also today. And then Grover's, and then today you have a whole slew of simulation of quantum processes using quantum computing. I think I'll have a little bit of time later on to talk about why we came from here to here and what's the relationship between these two areas today. So you hear today a lot about this. You almost not hear anymore about this one. We can talk about that. So the simulation is great thing because lots of practical applications where this is required and you can do that, but it's simulation of quantum processes. Well, simulation is not a great term when you try to get money out of the program managers. They want to have quantum computing, so the smart managers, they invented a new term. Now the quantum computing is divided in two branches. First branch is the original one. It's called the gate-based quantum computing, which requires a sequence of control node gates to do the calculations, that is capable of doing the Shor's algorithm. And it is called the Hamiltonian-based quantum computing, where because this simulation is simulating the Hamiltonians of those systems. That's what you do. You take your machine, you run this quantum simulation, and it spits out parameters that otherwise you will need to use big computers to solve large system of differential equations to describe the parameters of the system. Because like you have a chemical or biological objects, in principle you can describe it. You can derive so many differential equations, how many degrees of freedom you have in this system. And we all know that if you have a system of differential equations, the regular computers can solve that. Question is how long it would take. Because if the system has 1,000 degrees of freedom, this would be 1,000 of equations, matrix 1,000 by 1,000. So that's the biggest problem. That's what, when you heard about the quantum supremacy, that means this solving the huge system of differential equations on a classical computer versus building a quantum simulator to achieve the same result. And the question, which one is faster? That's basically what all the essence of modern quantum computing, what you hear and read in the literature today. And by the way, pay attention how many times you may see something like real gate-based quantum computing for the Shor's algorithm. There will be interesting statistics. Okay, how we usually model the qubit? Well, it's a wave function. It's a two states, 0 and 1. And this is amplitude alpha, amplitude beta. If you measure the state 0, then the probability of finding your system in the state 0 will be proportional to the square of this amplitude and 1 square of that amplitude. It's a standard procedure for any quantum system and measurement of any quantum system. Amplitude will be squared and then gives you probability to discover that system. Well, if you have the 2 qubits for 2 systems, then it will be product of 2 psi of A, phi of B. So 2 qubits. Why I'm saying 2 qubits? Because we'll really need 2 qubits. 1 is good, but it's not enough for entanglement. Well, what you can do with qubit? The qubit operations, well, when Wolfgang Pauli introduced this, he didn't think about quantum computing. He was thinking just spin operations. And of course, spin can be up and down. It's a binary entity. So since it's binary, you can operate by 2x2 matrices. So this is the Pauli matrices that operates on spins. and can do transformations, and we'll see how useful they are these days in the quantum information processing. Okay, and well, this is Pauli, and who is this? Do you know? It's Bohr, and what they doing? They throw in the dice, right? You've heard of all this story that God not playing dice, you know. And it was all big discussion about the probabilistic interpretation of basically quantum mechanics and its probabilistic character. It all goes. It was the first time when people got kind of clash of conflict of personal normal perception of the human being, which is fully classical, we live in the classical world, and the theory that deals with amplitudes. You cannot see the amplitude. The same way like in electromagnetics, you cannot see the vector potential. You can only detect the field, actually not only the field, the square of the field, right? So it's kind of hard, this was the reason for so many discussions and still going on discussion in philosophy about that. Well, I mean, this representation of the qubits. So this is one qubit. This is one state of the qubit. This is the second one. Basically, what you can do, you can use the Pauli matrices to change those qubits. So you just act. This is your qubit. This is the matrix. That's an answer, and it's just interesting combination. Basically, this is the phase flip, a Z matrix, X gate. It's a quantum NOT gate. It's a bit flip, basically. Then Pauli Y gate is both phase flip and a bit flip. So just an example of the algebra. Well, there are two other very important 2x2 matrices in quantum information exist. So there is a phase gate, the one that gives you just phase shift, and Hadamard gate. Hadamard gate is very important for us. We'll use it many times in this course because in optics there is a great device that executes Hadamard gate is the wave splitter. That's 2x2 device, which later on at the last lecture I'll show you our latest development that we discovered you can do much better than wave splitter, simple wave splitter. So that's what you can have, and what Hadamard gate does, it gives you superposition of state. Superposition is very, very important for the entanglement that we will talk later on, and that's what the Hadamard gate. So you start with gate applying to 0 state, but then you have the superposition of 0, 1. You apply to 1, you have superposition of 0, 1 with the minus sign, and you can of course go in reverse because it's all unitary. Well, entanglement is the maximally entangled 2-qubit state. So entangled state is a state of 2 qubits, of 2 particles. Remember, to have something non-separable, you have to have the 2 entities at least, right? So in our case, our entities are qubits. 1 qubit, 2nd qubit, and you can put them together in such a way that it will form a non-factorizable combination. Well, it happens to be that 4 of these combinations, like here, are very useful in quantum information processing and in photonics as well, because they form a base of Bell states. Any of the states of 2-qubit states can be represented as the superposition of projections on these 4 states. Because what is the base state in quantum mechanics? In any space. So the base, like in our normal world, is x, y, z, right? And every vector in our world can always be represented as the superposition of 3 projections on that, right? In quantum mechanics, it's not 3, it's many. It's not necessarily spatial, it could be any physical parameter. That's kind of tricky part, you have to twist your brain a little bit. Mathematicians are better equipped for that. Physicists have to train your brain to do this. But it's possible, so this is very useful, and it's used for many quantum information processes. What's important here? I say this first time, but I will repeat it again and again in several places. And the point is, the reason I'm doing this because I'm an experimentalist. I know this just by heart. Lots of theoreticians, they kind of brush it away. They don't pay attention to this. But 0 and 1 here are logical 0 and 1. But they're not physical 0 and 1. This 0 means it has to be some real physical parameter between this that you can assign value of 0. For example, it could be two-level system, energy system. One level is 0, another level is 1. Or it could be photon with polarization. This would be my 1, this would be my 0. But you always have to have energy associated with each of these elements of the state, because otherwise you cannot measure that. Remember, in order to measure something, to get information, you have to have an energy detector. What helped me a lot many years ago, one of my colleagues, a very, very old theoretician, he said, remember, there is no information transfer without the transfer of energy. Sometimes people say, oh, I know what's in there. No, you don't know until the energy comes your way and you detect it. Until it happens, you just can guess what is there. It's not information, it's just a guess. Okay? So, with the Pauli matrices, you can X, Y, and Z, so you can apply them on different, so there are two qubits here, first, second, and you can apply, and you can move between all these states. So you apply X to this state, which is 0, 0 plus 1, 1, it ends up 0, 1 plus 1, 0. So from phi plus state, you go to psi plus state. If you use Z and apply on the second bit, you get transformation, so you can go back and forth with Pauli matrices. Pauli matrices is natural operator moving around the qubit space and entangled space as well. Well, sometimes, I don't want to go much in there, but I really have to touch this. Remember, the entanglement is for multiple particles. We just discussed 2, but it's not necessary to be 2. It could be 3, 4, and more. So if you go for 3, you can design non-factorizable states of 3. The only problem with that is,
if you lose one particle, you will lose everything in J system.
well, that's always true. That's always true. But here, when you don't lose anything, even on the paper, it's in theory, you have too many options. Remember, your space, availability of states is growing. To operate this to verify these GHD states, if you look into the papers where people did this, how many tests you have to make to verify that this is a particular state. In 2 particles, you need basically 2 by 2, 4 measurements. Here you would need up to 256 measurements to do full characterization of the state. Well, actually for 2 by 2 you need 4 by 4, 16 measurements. 16 and then 256. Okay, so that's, it's just to show you what's the difference between separable state and non-separable state. For example, this state is separable. Why? Because you take this state, and then this 1A and 1A you can take out of the bracket, and this is the second one. So now you have one state, and this is superposition state. So this is a product of 2. So it's not really entangled. It's a product of 2 other states. You can find which ones. Okay, and this is just another example of the product state. So that's the difference between factorizable and non-factorizable. Lots of exercise in this area you can play. Okay, so now let's go back to issue of many and not many and two. So originally, Schrödinger introduced that in 1935. And you all know that Einstein, Podolsky, Rosen in 1935 wrote a paper questioning the quantum mechanics and its completeness, right? And they did that based on the entanglement. We'll come back to this topic many times, a couple of times later today. But let's just look at this. So you have a wave function of two particles, but these two particles could have multiple variables. And basically, as you can see, this is the superposition from n equal 1 to infinity of how many variables you can have associated with each particle. It's an infinite sum. When you look at that, and this represents the entanglement, the same as before, as I told you about non-factorizability, it's all very mathematical. From the standpoint of physics, of researchers, especially experimentalists, it's very hard to kind of grasp. Thanks to David Bohm, then he did it using spins and explained it in a very simple version right here. So if you have two particles with spin up and down, and total spin is 0, then you can have only two options. Option 1, up, down. Option 2, down, up. Okay? So now, this is the example of entangled state. When you look at this state, what you can see? First of all, and this really helps you to understand what does it mean to have entangled state of two particles in physics, in reality, in experiment, and how to deal with that. For me, that was the beginning of the how to learn to design entanglement in the future. So what do we need? We need first, you see this term, and they are equally weighted, which is called superposition, right? Two options, absolutely equal, 50-50, and another term comes with that is indistinguishability. Perfect superposition, you cannot distinguish between two options. And what else is important here? The sign between them. What does it mean, sign between two terms in quantum mechanics? Phase is stable. Because if this phase term will start fluctuating, actually I have to put here e to the I phi. And if phi is fluctuating, at the end that was the mixture, it will be product stable. It's not entangled anymore. So you need two conditions, superposition and stable phase relationship between these two options, right? In physics, stable phase relationship between any two entities, what it is? What's the definition of that? If you have this effect, and there are stable phase relationship between them, like take electromagnetic field. Coherence, exactly, that's coherence. Well, coherence is a feature. How do you usually measure the coherence in physics, in experiments?
You take a reference field.
Correlation. So I call it correlation simply because I'm experimentalist. That's how you reveal this, but degree. So you need the superposition and correlation or coherence. And that's two conditions that you have to create an entanglement. And so two conditions that exist in the entanglement, in the good entanglement. That's two conditions you have to perfect if you want to have a good demonstration of the entanglement. And we'll talk more about this later on. Okay, and this is just to show something that we will study later on, how to make this using parametric down conversion as a great source of entanglement. Well, again, generation of Bell states. You can have spin states, up, down, up. You can have polarizations. Here, I especially would like to point out this one. Because there is small branch of theoretical work in this direction and arguments going on, people saying, oh, you can have entanglement of a single photon. Well, you can have superposition. But you cannot have really correlation of single photon. Do you know why?
What is the thing that I should correlate it to?
Exactly. What is the correlation? You do measurement of one option, of second option, and compare them, because correlation is always revealed through the joint probability of event, right? The conditional wave probability versus probability of separate events. That's how you delineate correlation versus no correlation. It's a standard. So if you have single photon goes here or there, yes, it's superposition. You put it on the beam splitter, 0 here, 1 there, 1 here, 0 there. Looks like entanglement, 0, 1, 1, 0, but there is no energy behind this 0. It's empty. Why you cannot really, why it violates our definition of entanglement? Well, the formula is 0, it means no energy, it's a vacuum. Vacuum doesn't have a phase. It's a random phase, right? So it immediately erases the stable phase relation between them. Not talking about the fact that you cannot measure the vacuum, really. So you put two photodetectors, sometimes it's here, sometimes there, but you don't know they're correlated or not. So basically just, again, another piece of kind of removing mystery from quantum mechanics, really, because if otherwise it would look slightly mysterious. Okay, now we're coming to the Gauss inequality tests and how to reveal the presence of entanglement. And it's important because also it's related to two things, basically to Einstein-Podolsky-Rosen so-called paradox, and to many discussions, and even the Nobel Prize recently. So the idea is you have a source in which you have two particles such that there's a limitation on their spin. So total spin is 0, so it could be 1 up, 1 down, down, up. Two detectors, you have an apparatus at different angles measuring projections of the spins. So, and then the probability of projections will be defined by the simple equations of projections of vectors. That's what it is. Basically, it's spin or polarization is the same. It's always like if you polarize it like this and polarization is at the angle, the result is proportional to the cosine. So it's projections. And probability is the square of those projections. And you can measure different things. And as I said, the Nobel Prize was awarded for these first tests. John Clauser was the first. Then Alan Aspect was doing his experiments when in 1980, 81, we'll see the apparatus with what parameters. And Anton Zeilinger, at that time, he was working still with neutrons, and then he moved into the photons. We had lots of interesting results together as well. So what is the idea? The idea is very simple. You have a source, two detectors here after the analyzers, and the difference is what quantum mechanics tells you is a projection of vectors. What the classical mechanics tells you that probability will be bounded by -2 and +2 because it will be just product of events. It's between dependent events or related events. One thing comes from with this, it's a so-called Einstein-Podolsky-Rosen paradox, and I especially would like to use this picture for this to resolve this paradox basically, because how the paper was and the whole situation was presented. Like they say, okay, let's have two space-like separated detectors. Like one is here, one is there, pretty far away. And then you have entangled state coming here and coming there, and let's detect this, you have the results. How come? Paradox. How this one knows that this one is supposed to be the other way? Non-locality. We all know that non-locality doesn't exist. My usual question when people talk about non-locality, give me a definition of non-locality. If you study physics from basics, you know that non-locality means something moves faster than the speed of light. Information moves faster. And we all know it cannot be. So why don't you use the term non-locality when it's everywhere in the literature when it's not there? Okay? But the point is very simple. And I was as much confused as everybody else. Actually, that's additional discussion, like why people use those paradoxes. Just to get researchers in the field, but when you realize there is no paradox, it's too late to change the field, basically, to stop in there. So, source. Basically, the point is, remember I told you about the closed system, the basic postulates of quantum mechanics? If I consider only this and that, I leave the source outside. It's a violation of basic principles of quantum mechanics. Because energy comes into your system, to your detector, and you don't count this energy. And then, basically, you're trying to say that quantum mechanics is not complete when you just violated the basic principles of quantum mechanics. And source is usually, source is where you make your entanglement, and we'll just have this whole lecture on how to make this by proper experimentation. Nowadays, we know everything in entanglement. It's not a paradox and not fancy things anymore. It's just tool for engineering. So it's always localized. It could be atom, it could be nonlinear crystal, it could be anything, but it's local. Okay, it's local. Then, when you have radiation of like electromagnetic, I'll talk about photons today, but for particles it's even easier. For photons, so it's electromagnetic field going this way. The propagation of the electromagnetic field in vacuum is deterministic. What does it mean, deterministic? If I know what it is here, I can predict where it will be anywhere in the vacuum, because nothing disturbs the field, right? Propagation of the field is well defined by the Maxwell's equations, the wave equation. So if I know what it was here, then I know, if, for example, if I measure it here, I know where it was right there. It's all predictable, it's deterministic, absolutely information-wise. And then you start measuring, the measuring procedure is also pretty straightforward. But the other thing is, just also, to verify that this result is true, you have to take a result of this measurement and bring it together with this, and compare and measure the joint probability. So your system is closed from here to here, is all, there is no any room for non-locality here. It's all local. But what's the difference between these two? What kind of state you prepare? That's it. You prepare the classical state, that's what you will have. You prepare the really nice, clean quantum state, you have maximum violation here. You prepare so-so quantum state, you will be in between. In the lab today, my students, they're using Bell's inequality violation to see how clean the state they prepared, basically. That's what it is. Well, another interesting thing is, the difference between classical, correct, and quantum mechanics happens only at particular values. In maximum values here, here, and here, they completely coincide. You really have to find this level, these particular places where the difference between cosine square curve and linear curve is maximized. And that's why the 22.5 and 67.5 degrees are so where they're coming from. Okay, Alan Aspey did this with atomic cascade decay, the system that gives you two photons with two polarizations. Well, so everything is great. It's just, you know, when you have a system that is tiny as atom, then momentum conservation requires the photons can go anywhere, 4 pi, right, out of the system. So the atom has to be in the clean environment. It's usually cryostat with windows. The flux is very low. That's why it really took a while for them to get a good statistics. So the source, so this is the divided polarization. Then these two modulators, they were used to change polarization on the fly, and so on, lots of different variations of Gauss inequality tests. And here we go. Yes, depending on the angle, you could have maximum violation at 27.5 degrees or 67.5 degrees, but anything around here is your classical system. You cannot distinguish classical from quantum here, only this is distinguished, and that's a room for distinguishability. And this room here depends on how clean the state you prepare, and we'll discuss more. It's not only how clean state you did prepare. The state can be modified or destroyed anytime from the source, propagation, and detection. It's another basics of quantum mechanics. You always have to consider, because you consider enclosed system, as long as it's quantum. So source is quantum, propagation has to be unitary, not disturbing quantum, and detection, it's where you end your quantum system, you project it on the classical one. So all these things, in principle, can spoil your entanglement and affect these results. That's why people talking about the because your particles can be absorbed or lost on the propagation. That's why people say, oh, you haven't detected all the particles. That's where the fair sampling argument is coming. So basically, if your photons are going randomly, the fact that some of them randomly got removed from the flux does not change the overall distribution. Then quantum efficiency of detectors, basically the photons come in, but not all of them are detected because quantum efficiency is not 100%. That's another loophole in all these arguments between that. So basically anything can reduce this margin, but this margin is very valuable because we'll talk more about this. This is one of the resources people use for quantum communication, for example. Well, and paramedic down conversion is one of the sources. I was using this in parallel with Alan Aspey back in Moscow when he was doing Bell's inequality violation. We were doing quantum metrology with correlated photons. So it's a process of nonlinear generation of two photons from the laser palm inside nonlinear crystal. Why it has to be nonlinear crystal? Why do you think? Why we cannot do linear crystal? Why it has to be nonlinear crystal?
You can generate two photons with linear crystal.
Well, yeah, the point is that, remember the electromagnetic field, when you do the primary quantization, photons are, it's another subject of discussion that what are the photons? Photons are not really particles, they're quasi-particles, right? Even procedure of quantization of the photons is different from quantization of particles. You have to do it in two steps. The first step is truly classical. You just take the wave equation, boundary conditions, and calculate normal modes, right, of the field. And by definition, those normal modes, they are orthonormals, which means no energy transfer between them. They are orthogonal. In order to establish any kind of motion of energy, and the fact that frequencies are different because h omega is the energy here, it means you have to do something non-linear, right? You have to bend the rule of the linearity of the system, and that's what happens inside this non-linear crystal. That's why energy from here can flow in the energy of these two modes. And it's local, absolutely. So basically, at every single point here, at micro volume, it can happen. But if you take micro volume here, micro volume here, micro volume here, as I told you, the smaller the volume, the more uncertainty of the k vectors, right? But there is a condition that is called the phase matching condition. If the phase velocity of photons coming from all of these elements in some directions sums up, you can see amplification of, not amplification, summation of that result. Otherwise, it will be a random kind of background, basically. And that's very interesting, one interesting point I want to make here. We all have, many of you have seen this. This is they say, okay, this is the energy conservation, this is momentum conservation condition that has to be satisfied in this crystal. And when someone say that, I immediately can see that this person comes from high energy physics, basically, or particle physics. Because in particle physics, scattering process is defined by that. In the nonlinear optics, these two equations are not two separate equations. They are one equation, omega over k, which is the phase velocity. And you really have to match the phase velocities, and the process of matching of velocities in particular directions is interference. It's equivalent to like you have water and two sources of vibrations with waves. You can see in some directions the waves are adding, in some subtracting. That's the same thing. Absolutely. It's just interference. That's what the phase matching condition is about. And the nonlinearity comes from the structure of the elementary cell of the crystal. It's made of particular ions, so the electric field inside twisted. It's not linear, and that's where things comes about. Okay? And what it can give you when you have when this device operates in so-called spontaneous regime, from time to time, the energy of this photon can be divided in these two, and these days people call it spontaneous chromatic down conversion, because the frequencies of these two waves is smaller than the frequency of that wave. But in reality, it's not exactly correct, because originally people who study optics, they know that down conversion, the term has been reserved for a completely different process. And when this particular process has been originally discovered in 60s, not late 1960s, it had a completely different name. It's called, actually, three groups simultaneously discovered it in Stanford, in Cornell, and Moscow State University, and had three names. Parametric fluorescence, because you put one wavelength in and you have many going up. Parametric luminescence, same thing, one in, many out. Or parametric scattering of light, one in and it scatters to many different colors. It's only later the different term came 20 years ago. Okay, so that's what it is about. And what it gives you the correlation, because of they were born in this microscopic volume, they're basically simultaneous. Well, with the accuracy of like less than 1 picosecond. For any detector in the world, single photon detector, they will be simultaneous. Because there's no any detector that can distinguish the single photon detector that can distinguish the distance in time smaller than basically like 100 femtosecond. Okay, correlation in time. Correlation in frequency, well, because of the conservation of energy, of course. So this energy plus this energy should be equal to that energy. How well is it satisfied? Well, it depends on your pump. If your pump is highly monochromatic, very narrow band, it's very important because it leads to very interesting effect. Then this is very tight. So omega 1 plus omega, always omega, almost like double function. Okay? So correlation in frequencies. And correlation in directions. Correlation in directions defined by the interference. Well, it's basically depends on how long crystal you have, what dispersion you have inside, and together they will give you the shape of the distribution of the K vectors going out. It is called the phase matching curve of the device. Well, so what do we have? We have correlation in time, correlation in direction, correlation in frequency. How we can make entanglement? What's missing? Correlation is there. Superposition, exactly. How we can make superposition. And that's the subject of our original paper that we did with Anton Salinger in 1994, published in 1995. So basically, if you take the type 2 nonlinear crystal, So all these rings are horizontally polarized, all these rings are vertically polarized. And position of those rings depends on the orientation of the crystal relative to the pump. And if you put it in a particular position, then you will have a situation like this. And what the points of interest are right here. You see the color is the same, indistinguishable. The distance from the center, the direction is the same, it's indistinguishable. And you don't know, and it's always one photon here, one photon there, because there has to be a conservation of momentum relative to the center. The pump is right here in the middle, it's blocked. So, so one photon here, one here, and now you don't need to know whether this one is from the top ring and this one from the bottom, or vice versa. There's HV, VH, VHV, VH. So we create a superposition. And that's basically the immediately boosted up the rate of entangled photons you can create, and has been used so many times in so many experiments. Basically, that's what it is. I think, let's see, I think we're pretty much done with the first hour, right? I hope you still have enough strength to come back after the break for the second one. And we'll continue after that, unless you want to have answer questions. I don't know about answer questions. Do you want to have them after each lecture or after all lectures, whatever it is?
Perhaps now let's take a short break, and after break, maybe questions.
Okay, okay.